Hi, I'm Sean DeGrace, and I'm doing problem number 21.79, dealing with strength of the electric force in the University Physics textbook by Young and Freedman. The problem states that imagine two 1-gram bags of protons, one at the Earth's north pole and the other at the south pole. Part A is how many protons are in each bag. In Part B, it wants you to calculate the gravitational attraction and the electric repulsion that each bag exerts on the other. And Part C, are the forces in part large enough for you to feel if you were holding one of these bags? For step one, I drew the problem to help you better understand what it's asking. And so we have the two bags separated by the distance of the Earth. And so for part A, it's really asking you how many protons does it take to equal a gram. And to find that out, we have to take the number of protons times the mass of a proton to equal 1 gram. And since the mass of a proton is constant, we can just look it up and find out that it's about 1.673 times 10 to the negative 4th grams. Now if we divide 1 gram by the mass of the proton that we just looked up, we find that the number of protons in 1 gram is 5.79 times 10 to the 23rd. So about 6 times 10 to the 23rd protons are in each 1 gram bag at the poles of the Earth. Now in part B, I split it up into 2 parts, first calculating the electrical force and then calculating the gravitational force that each bag exerts on the other. So first I did the electrical force, and with the electrical force it is going to be repulsive because the protons are of the same charge and they're both positive, so therefore they're both going to repel each other. Now to solve this problem we are going to use Coulomb's law, and we're mainly dealing with both the electric force and the gravitational force. We're dealing with a lot of constants. There's not a lot of calculations we need to do. So in this equation, F equals 1 over 4 pi epsilon naught times Q1 Q2 over R squared. Now that 1 over 4 pi epsilon naught is just it's just a form of the permittivity of space, of free space. And so that's just going to equal some number. And then that R is the distance between these two bags of protons, which is going to be the diameter of the Earth. And so all we really need to figure out is Q1 and Q2, which is going to be the total charge of, for Q1 it's going to be, let's say, the total charge of the bag at the North Pole, and for Q2 is the total charge of the bag at the South Pole. So, as I said, that 1 over 4 pi epsilon naught is a constant, which turns out to be just about 9 times 10 to the 9th. Now, don't be confused that R is actually diameter. So the diameter of the Earth is, let's see, 12,765,200 meters. Now, I looked up the charge of a proton because that is something that's constant, and that equals 1.602 times 10 to the negative 19th coulombs. But to find the total charge of one of those bags, you have to multiply the charge of a single proton times the amount of protons that you have. And since we calculated in part A that we have just about 6 times 10 to the 23rd amount of protons, we must multiply the charge of protons by that amount, which equals 96,120 coulombs. Now, the bag at the North Pole and the South Pole are both protons and both contain the same amount of protons, therefore they are equal. So Q1 and Q2 are equal. So we finally bring everything together. We have our form of the permittivity of space, which is 8.988 times 10 to the 9th times Q1 times Q2, which is that 96,000 number times itself, and then divided by our diameter of the Earth squared. And so using that, we get 5,009,607 newtons. But now it's our job to find out what the force due to gravity is. And just like it was repulsive due to the nature of protons, with the gravitational force, it's going to be attractive by the nature of the gravitational force. And so to solve this problem with the gravitational force, we are using, surprise, surprise, Newton's law of gravitation, which states that the gravitation force is equal to the gravitational constant, which is just like it says, a constant, times the mass of the first object times the mass of the second object over, once again, the distance squared. So that's going to be the diameter of the Earth. And so the constant, the gravitational constant, is 6.67 times 10 to the negative 11 newtons times meters squared over kilograms squared. And so then it gave us in the problem that our bags were 1 gram, but to do this problem we need to convert that into kilograms. So it's just going to be 0.001 kilograms. And like we stated in the first part of part B, the radius of the, the diameter of the Earth is 12,765,200 meters. So like last time, we're going to put everything together, and so we have our gravitational constant, 6.67 times 10 to the negative 11, times our two masses, mass of 1, mass of 2, mass of the bag of the North Pole times the mass of the bag of the South Pole, over our diameter of the Earth squared. And so that equals 4.09 times 10 to the negative 31 newtons. And for part C, it's pretty clear that with the electrical force, we would be able to feel that immediately, and it would be very painful if we were holding on to that, and that the gravitational force due to the bags wouldn't even affect us at all. And so, thank you for watching.